In this video, I'm going to show you how to draw Haworth projections, which is what we use in order to represent the cyclic form of carbohydrates. We previously learned how to draw the open chain or acyclic form of carbohydrates, and that was using a Fisher projection. Here we are going to talk about Haworth projections. So first, we're going to start with our open chain or linear or acyclic form of our carbohydrate. All of those terms mean the same thing. And then try to visualize this carbohydrate as being rotated over on its side, where now carbon 1 was here, and now it's over here on the right-hand side, and carbon 6 is now on the left-hand side. So now imagine grabbing this oxygen here that is highlighted in red, and bringing it around where you are bending the structure as it's being shown here, so that now this OH, which was over here on carbon 5, now this OH group is near to your carbonyl group. The reason we are doing this is because when that OH group is near this carbonyl group, now they are going to be able to react and form a bond. So before we form that bond, I just want to show here that how these Haworth projections are interpreted is that this solid dash here means that the front of this cyclic structure is pointing towards you, and this is going behind you. Okay, so you can imagine this ring as being kind of like on the plane. And then these hydrogens, for example, are pointing up, as well as this group here, and this OH and H, all of these are pointing up above the ring. And these OH groups here, along with this H and this other OH, are pointing down or below the ring. So I will often refer to, for example, this OH group as being below the ring, and this one being above the ring. If we look at this group here, this group is above the ring, and this group, this hydrogen here, is below the ring. Each intersection here is going to be a carbon, very similar to how we interpreted skeletal structures. All right, so we are here, where I have now basically bent my linear chain and moved it around like this, so that this alcohol located on carbon 5 is now near my carbonyl group. The reason I'm doing this is because this oxygen can form a bond with this carbonyl carbon, as shown here. And this is what's going to form this cyclic structure. So what is basically happening here is that this H is going to come off, one of these bonds is going to break, and then what you'll be left with is a bond between this oxygen and the carbonyl, what used to be the carbonyl carbon, and that's the bond being shown here. And now your oxygen has only one bond to it, so it's going to pick up a hydrogen. And that is how we get, and that is how we get this hydrogen here. So this is a type of reaction that we didn't exactly cover, but you can see that there are some similar elements here. We are going to be learning about a new group that's called the hemiacetal on the next slide. But right now, the thing to note is that this carbon here is what we call an anomeric carbon. And this is going to be important in determining whether we have what we call an alpha anomer or a beta anomer. And I will define that more in the next slide. So the point here is that when this reaction happens, you form a bond between the oxygen on carbon 6, which was this oxygen here, and your carbonyl carbon, which is this one up here. And that happens by bringing the molecule around and in close proximity. So when you do that, let's clean this up a little bit. Now you have a cyclic structure, but when you break this double bond here in this oxygen, this carbonyl group here, when you do that, you have the option of placing your new OH group either below the ring, again relative to the ring on this carbon, or above the ring, shown in blue here. And whether you place it below the ring or above the ring, that is where the term alpha or beta anomer will come in. They will define which one is which. You can see here that the alpha anomer has that OH group pointing down, shown in red, and the beta anomer has the OH group pointing up. And that is how we would be able to classify the two. Then you'll notice that this CH2OH group is always drawn up or above your cyclic structure, and we will go into more detail about exactly how to go from a linear form to a cyclic form. The point of this slide is to show that we can actually interconvert between a cyclic form and an open chain form. Okay? And it is this oxygen on this carbon that is doing the reaction, and that will be part of your six-membered ring. This type of cyclization reaction, it exists in equilibrium, so it means it's interconverting. It's a dynamic process, and this is called mutarotation. But what this means is that your cyclic structure, so this closed structure, is actually going to be the major form in a solution of glucose, for example. You can see that about 37% is going to be in the alpha anomer, so that's when the OH is pointing down, and 63% will be in the beta anomer, okay, and this is for glucose. What you're also going to see is that your acyclic form, or your open chain form, that is going to be less than 0.02%. So yes, there is some open chain structure in your solution, but it's going to be a very, very small percentage. Now let's go back to that anomeric carbon that we were talking about. The anomeric carbon is going to be this one here. The reason we have a special name for that is because that's the one that's going to tell you which anomer you have. The OH pointing down is the alpha, the OH pointing up is going to be the beta. That anomeric carbon is also a hemiacetal carbon, meaning that that carbon is part of what we call a hemiacetal functional group. This is a new functional group that we have not covered yet. So how we define a hemiacetal is basically the carbon, so you locate a carbon that has an OH group and an OR group attached to the same carbon. So if we look at our cyclic structures here, whether we look at the alpha or the beta anomer, what you're going to see is that this carbon has an OH group and an OR group attached to it. The R group here happens to be a cyclic structure, but it's the same idea. So this carbon here, because it has an OH and an OR group attached to it, that is called a hemiacetal. This is to not be confused with an ester or an ether, for example. Okay, so those are some definitions and some new functional groups that we will be encountering. All right, so how do we go from a linear structure to a Haworth projection? So we're going to start first with looking at where our starting point is acyclic aldohexose. So again, recall an aldo means that I have an aldehyde in my sugar or in my carbohydrate. Hexose means I have 6, hex means 6. I have 6 carbons in the sugar. So the first step is, I would say the very, very first step is to go ahead and number the carbons on your open chain. I would always start with this one so that you can keep track of all of your atoms. Always start with the one at your aldehyde group, or if you're dealing with the ketose, near the carbonyl group. We'll talk about that when I show you how to do this for a ketohexose. All right, so first just number your open chain. Now let's place the oxygen atom in the upper right corner of your hexagon. So aldohexoses are going to form 6-membered rings. But these 6-membered rings are not going to be all carbons, as we have seen so far. One of the locations on your ring is going to be an oxygen. So in terms of position here, you will see that you have 1, 2, 3, 4, 5, 6 points in your ring, but one of those is an oxygen. So the 6-membered ring is composed of 5 carbons. So you're going to have 5 carbons and 1 oxygen. So your 6-membered ring is composed of that. Okay, so first you're going to put the first member, which is that oxygen, and then the remaining points here are going to be carbons. Okay. Then the next thing you want to do is at the carbon that's to the left of your oxygen, there you're going to add your CH2OH group. Okay, remember your CH2OH group is not a chiral center, so we're just going to put that above the ring. It won't need a particular orientation. Okay. So that is the very first step. Just write in your oxygen into the 6-membered ring, and then complete your 6-membered ring with carbons, and then draw your CH2OH group above your 6-membered ring. The next step, now that we have already drawn our CH2OH group above the ring and we have our oxygen in the upper right-hand corner, now we need to think about our anomeric carbon. This carbon here is that carbonyl carbon here. In this case, it's from the aldehyde. So that is the one where the bond is breaking, and this oxygen here is coming around to bond right there. Okay, so that is how you get this cyclic structure. Okay, so let's clean this up. So your anomeric carbon is the one that is going to define whether you have an alpha anomer or a beta anomer. Because when you break this double bond here, you have the option of adding your OH group either below the ring or above the ring. So the next step is to locate that anomeric carbon, which is always going to be to the right of your oxygen in the ring. So this is going to be carbon number 1. This is carbon number 2, 3, 4, 5. So now I'm here. So recall this is 1, 2, 3, 4, 5, and 6. So this 6 carbon here is the one that has that H2OH. So carbon number 1 is going to be your anomeric carbon. So this is the next step. Just decide whether you have an alpha or a beta anomer. Once you have done that, you have placed your oxygen on the upper right-hand corner. You placed your CH2OH group on the carbon that's to the left of that. You identified your anomeric carbon, which is the carbon to the right of that oxygen. Then you placed your OH either below or above the ring. Now you need to place the remaining substituents. So now we are looking at carbon number 2. So remember, this was carbon 1, this was carbon 6. So now we're looking at carbon number 2. The rule here is that the OH groups that are on the right-hand side of your structure are going to go below the ring, as shown here. Those that appear on the left-hand side of your Fisher projection structure, those are going to go above the ring, as shown here in blue. So if I am drawing this from scratch, I would see that in carbon number 2, my OH is to the left-hand side. That means I must draw it above the ring. And then for carbon number 4, OH is on the right-hand side, so I will draw it below the ring. And this is why it's important to number your carbons so that you make sure you are placing your oxygens or your OH groups in the proper orientation. Because again, remember, since these are chirality centers, it is important to place them in the correct orientation. Let's do an example. I have written the rules that I just went through. I kind of summarized them here to kind of help us work through these problems. All right. So again, the very first thing I will always do is number my Fisher projection formula or structure. And then recall that each cross there is a carbon at each cross. Okay. So I recognize this is an aldohexose. And the steps we just discussed are specific to aldohexose, although there will be a lot of similarities to the ketohexose, which we're going to cover next. But I recognize it's an aldohexose, so I know I'm going to follow these steps. If I have an aldohexose, I am going to form a 6-membered ring. So if I'm forming a 6-membered ring, I know that one of those members is going to be an oxygen, and then the others are going to be carbons, and they will be implied at every corner. So I have my ring. I have already done this part. Now I need to add the CH2OH group, which is this one down here at carbon 6. I have to add that pointing up on the carbon to the left of my oxygen. This group pointing up is specific to D sugars. Remember, this is a type of enantiomer, and we are mostly going to deal with D sugars, and so we're just going to always point it up or draw it pointing up unless we need to do otherwise. All right, so that means I'm going to locate the carbon to the left of my oxygen, which is this one, and I'm going to draw that CH2OH group above the ring. So again, this is carbon number 6. Let me draw that in a different color. This is carbon number 6. This here is carbon number 5. And if I look at carbon 5 here, I see that I have a CH2OH group bonded to that, which is what I just drew here. Then I also have a hydrogen bonded to that 5th carbon. So there's a hydrogen pointing down, since that CH2OH group is already pointing up. And then there's an OH group on that 5th carbon. But remember, this is the OH group that created the cyclic structure. Therefore, this oxygen here is this oxygen there. So you can see that this carbon 5 here has an oxygen bonded to it, which it does on your Fisher structure. It has a CH2 group bonded to it, and then an H group bonded to it. Okay. All right, so now that we have drawn our CH2OH group above the ring, now we can go ahead and locate our anomeric carbon, which is going to be the carbon to the right of that oxygen, this one here. So now I can decide whether my OH group is going to go pointing up or pointing down. Let's say I want to do, I don't know, an alpha anomer. So that means that if I want an alpha anomer, that OH group has to point down, and then the H will point up. And again, this is going to be carbon number 1. And at this point, I would go ahead and number your ring, because this will allow you to keep track of all of your substituents. Okay, so I have done carbon number 1. So now I am ready to add the remaining substituents, which is carbon 2, 3, and 4. Remember that 5 we have already done. Okay, so now I need to think about whether my OH groups are on the right-hand side of the Fisher structure or the left. If they are on the right-hand side of my structure, I will draw them pointing down on my ring. So that means at carbon 2, this is to the right, so I'm going to point this down. And I'm just going to do all of the OH groups first, and then I will just draw in the hydrogens to satisfy the octet rule. So on carbon 2, I have an OH group on the right-hand side, so I'm drawing it down. On carbon 3, it is also pointing down since it's on the right-hand side. And on carbon 4, it will also point down. At this point, you don't have to draw in the hydrogens. You can draw Haworth projections without hydrogens, meaning that they're just going to be implied, similarly to when we drew skeletal structures. But here we are going to draw them in since we are learning how to do it, and I just want to make sure we're keeping track of all of our atoms. So this is a Haworth projection of this cyclic structure here, and this is specifically the alpha anomer. If we wanted to draw the beta anomer, we would do the exact same thing. So here's your 6-membered ring. The only difference, so this is CH2OH above, you would do the same. The only difference would be the orientation of your OH group at the anomeric carbon. So at this point here, the OH would point up, the H would point down, and this would be an example of a beta anomer. Okay, so that's how you can draw the Haworth projection of a aldohexose. Now let's look at a ketohexose. So what if we start with a carbohydrate that has a ketone instead of an aldehyde, and that ketone is located on carbon 2. So here we have 1, 2, I'm going to continue to number this, 3, 4, 5, and 6. So what we're going to do is the same idea. Now this oxygen here on carbon 5 is the one that's going to come around and bond to this carbon there. So this double bond is going to break, and this oxygen will want to pick up a hydrogen. So in order to do this, that's what's being shown here. You can see that this oxygen here, which is the one on carbon 5, is coming around and making a bond with this carbonyl carbon. So what's going to happen is this CH2OH group that is here located in carbon 1, that one will still be at this anomeric carbon, which is this group here. And then you will have an OH, from what used to be a carbonyl group, now that becomes an OH. And just like we did with the aldohexose, you can choose whether you want to draw the OH pointing up or the OH pointing down. If you draw it pointing down, then the CH2OH group has to go up and vice versa. Notice that there is another CH2 group here, which is this one on this side to the left of your oxygen. That is this CH2OH group here. Okay. So don't get confused between these two CH2OH groups. One is bonded to what used to be your carbonyl carbon, and the other one is bonded at the very end to carbon number 5. So let's go ahead and see how we would draw this kind of structure. Here are the steps as well for a ketohexose. You're going to see that many of them are the same, but there are some differences. So the main difference is going to be that a ketohexose is going to form a 5-membered ring. So you're going to have a 5-membered ring. So it's going to be a pentagon, but one of those is going to be an oxygen. That oxygen is this one here. So let's go ahead and number our Fisher projection so we can keep track. So now I'm going to draw this oxygen here. That's the one that's going to appear at the very top of my pentagon, of my 5-membered ring. And now the rest are going to be carbons. Okay. So now to the left of this oxygen, I'm going to draw this CH2OH group. That one will go up as well since we are dealing with these sugars. And then the hydrogen is going to go pointing down. Okay. Now let's take care of our anomeric carbon. Our anomeric carbon is to the right of this oxygen, just like we did for aldohexoses. The difference here is that now this anomeric carbon is not carbon 1, the anomeric carbon is now carbon 2. So this is going to be position 2 on my ring, 3, 4, 5, and 6. So that means I still need to draw in carbon 1. So now carbon 1 is attached to my anomeric carbon. So I have to choose whether I want to draw an alpha or a beta anomer. I'm going to go ahead and choose to draw an OH pointing up. And if the OH is pointing up, that means I have a beta anomer. So it's going to be a beta anomer. But now I do still have this carbon CH2OH group that I need to draw in. I haven't drawn that in yet. So that will have to go down. And therefore, this carbon here is carbon number 1. Now what's left is to draw in my remaining OH groups. I have one at carbon 3 and carbon 4 that I need to draw in. So the one at 3 is on the left-hand side of my Fisher projection. If it's on the left-hand side, I need to draw it pointing up in the Haworth projection. So I'm going to go ahead and do this OH, and then below will be the H. And then on carbon number 4, OH is on the right-hand side, so it will be below the ring. And that is it. That's how you draw a Haworth projection for a ketohexose. And the main thing to remember here is that you have a ketone. That ketone is, in this case, in carbon number 2. And therefore, you are going to make a 5-membered ring, along with having a CH2OH group on that anomeric carbon, which was one of the main differences from the aldohexose. In another video, we're going to go ahead and start with these Haworth projections in order to form disaccharides. And so we're going to look at the formation reactions using these cyclic structures. And then we're going to look at their hydrolysis reactions. And we will learn about a new functional group then, which is going to be the acetal. In this video, we learned about the hemiacetal. Then we are going to learn about a